Right. So we talked about waves last time. We went over kind of the basics of waves, and now we're going to start talking about what happens when you have more than one. So we're going to talk about, right, William? We're going to talk about superposition and interference first. There was a quiz today. Right. So in real life, like if you clap your hands, like I'm talking and clapping my hands at the same time, which I can do because I have a functioning brain. And me clapping my hands produces sound waves that go around, and me talking produces sound waves that go around. So this is just to say that in the real world, like whether it's sound waves or whether it's light waves or whatever, there's more than just one wave at any given place and any given time. So the question is how do we understand the interaction between two waves or between multiple waves of the same type? And so the way that we understand that is through this notion of superposition. So when two waves occupy the same space at the same time, they superpose. And so superpose is like the verb form of the noun superposition. And what superpose means is it just means that they add. Like they add up. So when I say add up, like you might think, well, what does it mean for waves to add? Waves are like physical things. How do you add up physical things? Well, so waves are described by wave functions. So given two one-dimensional waves, say f of 1 or f1 x of x and t and f2 of x and t, we can find the median, or we can find the what you would measure to be the disturbance in the medium by adding them up. Remember that wave functions just describe how much the medium is disturbed, so how much the pressure is different from the normal pressure from a sound wave, or how much the string is above its medium point, and so on. So the observed disturbance as a result of these two waves interacting is found just by adding. So the total disturbance is a function of position and space, or position and time, and it's just equal to the sum of the disturbances of the two waves that are moving through that space. And the disturbance, or the total disturbance, will also move, and it'll actually just look like two waves. So on the homework assignment that I'm going to put out today, one of the questions will be to show that the total, like the superposed wave, the total wave function, is also satisfies a wave. Satisfies a wave equation, and thus is a wave, even though it comes from adding together two otherwise unrelated waves. That's gonna I'll write it more explicitly in the homework, but I'm gonna ask you guys to do that. And that is true. If you have two waves, then the sum of those two waves, the sum of the two wave functions that describe that wave, is also a wave. That's interesting and not at all obvious, actually. So what this amounts to visually, if we're, say, imagining a wave on a string, is just lining up the two waves vertically and then adding up their disturbance magnitude. So this would look something like in the snapshot depiction, where we just look at a single instant in time, you'd have one wave, two wave. Let me draw them straight. If we add these together, we would get a third wave. So maybe this one's like this, and maybe this one's like this, and it's just like they don't have to be. Or you know what? Let me do it this way. This one's like this, and this one's like this. There we go. So then the sum of these two waves, and maybe they're traveling to the right or something like that. The sum of those two waves is just, it's literally just the sum. So the end result would look something like, let me try to line this up. Oh, that's terrible. This is so hard to draw. Okay, you know what? I'll do this. There we go. So the sum would look like this. I just added them up, and now the whole thing moves to the right. So that's actually not a stupid question. It's a question that that I was going to answer. But the point to make is waves have to be of the same type in order to interfere, or in order to superpose. Meaning that, like, generally one-dimensional and two-dimensional waves will be of different types. Like a 2D wave might be like an oscillation in a drum, and a 1D wave would be like an oscillation on the like on a string. And generally, unless they're connected in some way, they're not the same type of wave, so they won't interfere. Like, for example, a sound wave and a light wave can't interfere. A wave on a string and a sound wave can't interfere, although they can influence each other. Sorry, they can't superpose. I keep using interfere, and we haven't talked about that yet. So as another, so these two waves were moving in the same direction, and so they superposed in this way. And because they're moving in the same direction and they're in the same medium, so they have the same speed, this shape will remain constant, and it'll just move together as a whole thing to the right. But if you have two waves that are in the same medium moving in opposite directions, well, they can also superpose. But in that case, they will come together, overlap, do whatever that means, add up, but then they'll just keep going off in their own direction. They'll just split. And this is just to say that waves don't interact with each other. The observed disturbance is just the sum total of all of the waves passing through that point at that time entirely. But the waves themselves aren't actually, like, they're not affecting one another. They just pass through each other. And if they happen to add up, great. If they happen to subtract, also great. Yeah, this is actually precisely how noise canceling headphones work. They superimpose, or not superimpose, they superpose the inverse wave onto the incoming sound wave. That's exactly actually how it works. I mean, it's obviously a little bit more complicated, but that's the basic gist. So there are a few, or there is a, yes, this is why linear combination of atomic orbitals does work. Yes. Well, that's a more general thing, but yes, it is. So there are a few particular types of superposition that are super useful to study, and in fact, we're going to generalize those even further. So those types of superposition are known as interference, or is known as interference. And all it is it's just the superposition of two waves in a very particular way. So there's two types. There's constructive interference. And you may have heard these words before, by the way. So constructive interference occurs when the waves are perfectly aligned. So what that means is, imagine that you have two identical waves that are aligned. So one example would have been if this chunk of wave, if this chunk of wave would actually started out over here. Well, then they're perfectly aligned. And so the peaks are aligned with the peaks, and the troughs are aligned with the troughs if there were any. And so the resulting amplitude of the interfering wave is just the sum of the amplitudes. So in this case, the height of the resulting disturbance would be twice as large as the height of either of the constituent disturbances. Alternatively, let me put this back so that it's not inconsistent with my drawing below. Alternatively, I should just note that the resulting amplitude has the sum of amplitudes. Another type of interference, which you could probably guess, is destructive interference. Destructive interference is just the opposite. This is just when the peaks perfectly align with the troughs and the troughs perfectly align with the peaks. one and the other. And so the waves in that sense are exactly opposite, which just results in the resulting amplitude, or the resulting wave rather, has the difference in amplitudes. So if you had, for example, if we had a wave here, then the resulting wave would look something like, it would be a little small, because you take this height and then add to it a negative height. And so sorry, it shouldn't be that direction, it should be this direction. And so the disturbance is less than the original, than the biggest disturbance, and it's bigger than the smallest disturbance. It's the difference. And so that occurs when they are perfectly anti-aligned. And there's a particular type of destructive interference which occurs when the waves perfectly cancel. And when that happens, the resulting, and I'm going to put this in quotes because it's not really a wave anymore, the resulting wave has amplitude 0. Which is to say that the amplitude of the two waves were equal and they were perfectly anti-aligned. And we call this phenomenon, where you have two waves coming in and nothing coming out, total destructive interference, which sounds super cool. It just means that you have two waves coming in and no waves coming out. It just happens. Very strange. I mean, it doesn't happen often, which is why this happens. For constructive interference, do the two waves have to be identical, or they could have different amplitudes? Yeah, they can have different amplitudes, and that's true for regular destructive interference too. Like if you have one really loud wave and then one really small wave, if they're constructively interfering, the amplitude will just be a little bit bigger than the large amplitude wave. Similarly, for destructive interference, if you have one very, very small wave and one very, very big wave, the resulting amplitude will just be slightly smaller than than the amplitude of the big wave. It's only when the waves have equal amplitudes and they're perfectly anti-aligned that you get you get exact cancellation and total destructive interference. But this isn't all, right? So in particular, if we're studying a special type, is total, yep, that's precisely it. Yeah. So these types of interference are pretty typical for or are the ones that we are most interested in often, but we can actually generalize this notion. We can have like not perfectly aligned, not perfectly anti-aligned, but like somewhere in the middle. We can analyze that type of superposition as well, so long as we know something about the waves. So in particular, the waves that we can like most easily understand are harmonic waves. So what we're going to do is we're going to study general interference between harmonic waves. And the ideas will overlap, or the ideas will generalize to like more general waves besides just harmonic ones, but it's easiest to study them when they're harmonics. We just have like a formula for it. So we're going to do that now. So what we're going to do is we're going to try to come up with a formula that basically interpolates between the case where you have total destructive interference and perfect constructive interference. So I mean, when the waves are aligned, you're going to get twice the amplitude, right? And then when the waves are perfectly anti-aligned, you'll get 0 amplitude. So that number, the amount of amplitude that you get, should change with how aligned the waves are. And so we're going to try to understand that. But before we do that, I want to wax poetically for a little bit about what we're actually doing here. So from a physical perspective, like this is a physics class, it's not a math class. So from a physics perspective, the things that we're interested in measuring, things like the brightness of light or like the volume of sound, those things are described, or those quantities describe the intensity of the wave that we're observing, right? So brightness is related to the intensity of a wave, of a light wave, not the amplitude. I mean, the amplitude is related to intensity, but the thing that we're actually measuring is intensity. And the reason for that is because intensity is a measure of energy transfer, or rate of energy transfer. And so when we have a speaker, or when we're trying to measure volume, what we can do is we can ask the question, how much energy is our microphone detecting every unit or per unit of time. And that's precisely a power translation, or that's precisely a power measurement, and intensity is just related to power and area. So, or power and area, or power and length, and so on. Similarly, our eyes, if we're detecting light, the brightness depends on how much energy the cells in our eyes receive. And so the way that we detect, the way that we measure, the way that we quantify waves is by intensity. So what we're going to do is, rather than just studying how the amplitude changes between how the amplitude changes for when you have two interfering waves, we're going to study how the intensity changes depending on whether they're aligned, anti-aligned, and so on. So in general, we talked last time about how harmonic waves have 4 descriptive numbers, right? There's the amplitude, there's the wavelength, there's the period, and there's the phase constant. So in general, if I hand you a 2 harmonic waves, all 4 of those numbers could be different. So and we will study those differences, but we want to kind of narrow our scope to try to understand a particular phenomenon better. So for example, if the 2 waves have different frequencies, i.e. their periods are different, then because the wave speeds are the same, because we're assuming these waves travel through the same medium, they're the same type of wave, because their wave speeds are the same, their wavelengths would be different as well. Remember that wave speed is wavelength times frequency. And so if the frequency is different and this wave speed is the same, then the wavelength is also different. So we could, in principle, study interference of waves with different frequencies. But we're not going to do that yet. Interference of waves with different frequencies. And in fact, we are going to do that later when we start talking about sound. I think that'll probably be either this week or early next week. But we will do that. Not yet. It takes a little bit more work, but we will do that. We could also, in principle, study waves with different amplitudes. But that doesn't really teach us anything. We've already established that if the waves have different amplitudes, the interference effect is just minimized. It doesn't actually result in like something different happening. All that happens is just that the change in basically you go from like either full cancellation or doubling of the amplitude to slight decrease in amplitude and slight increase of amplitude. So it's a difference in scale, not a difference in kind. So we're just going to not worry about the case where the amplitudes are different. But again, the formalism that we are going to do today could be generalized to different amplitudes, and that's no problem. So the last thing that we could change is we could consider, what if the waves have traveled different distances? Or what if the waves have existed for different amounts of time? Or what if the waves have different initial phase constants? Well, all of those can be wrapped up in something that's called the total phase. And so the total phase is basically a way of representing how far along in an oscillation a wave is. And so the symbol that we use for total phase, the symbol that we used for the phase constant was a Greek lowercase phi. We're going to use the capital version for total phase, which is this. It looks like a regular phi, but with 2 lines above it, and it's straight. And so total phase just tells us how far along in a given oscillation a wave is. I'm going to actually write it 2 pi ft. And so as long as they have the same lambda, and as long as they have the same frequency, the only thing that would be different between 2 waves that have different phases is where the waves start, when they start, and what their phases are. You could imagine, for example, that you turn on a sound generator that generates a harmonic wave going that way at t equals 0 seconds, and then you wait 2 seconds, and then you turn on another one at t equals 2 seconds. And so in that case, the t for the, maybe we call the first wave wave 1 and the second wave wave 2, t0, it's a capital phi, it's a Greek letter phi. In that case, t0 would be equal to, t1 would be equal to t2 minus 2 seconds. So the total phase can be different if they are turned on at different times, if they started at different positions, that's x, or if they just started at the same time and the same position, but they had different phase constants. So we're just going to study what happens when they have different total phases, but they move at the same rate. They have the same speed, they have the same frequency, and so on. I need to adjust my notes after lecture. So we're going to assume that the waves are out of phase. The two harmonic waves that we're going to try to add together and all that means is that phi 1, which is the total phase of wave 1, does not equal phi 2, the total phase of wave 2. So you can just think of total phase as just like, it's a number in radians, and the capital or lowercase t represents, it's just the duration that the wave has been going for. Remember, this is a wave has an argument that depends on x and t. So x is how far the wave has gone, t is how long the wave has been going for. Right, so we have two waves. Sorry, it just zoomed out for some reason. So our two waves we have f1 of x and t. This should be equal to a times cosine of 2 pi x1 over lambda plus 2 pi ft1 plus phi 1. And so we can write that as just a cosine of the total phase. And then we have f2 of x and t, which is a cosine of 2 pi x2 over lambda plus 2 pi ft2 plus phi 2. Oh, this is, okay, I need to be extra careful here. Yeah. Actually, I'm just not going to write it as a function of x and t. That's better. And I'll explain the issue that I just ran into. This is a cosine of phi 2. Okay, so the issue that I ran into is that we want our function our functions to depend on x and t. Yeah. No. So the periods are the same because the frequencies are the same. Important point. Yeah, so we're not worrying about having different frequencies yet. We'll talk about that at a later date. And the same goes for lambda, for wavelengths. So the point is here, T1 measures the amount of time the wave 1 has been going. And similarly, T2 measures the amount of time that wave 2 has been going. Also, X1 measures the distance that the wave has traveled. And similarly for X2. So while they both are functions of some position, the number X1 or X2 might be different because the waves may have traveled different distances to get there. Like you may have started one wave here and another wave here. And so they're both going to travel, they'll travel different distances to get to the same place, right? And similarly, they will travel different times to get to the same place. Anyway, so that's what X1, X2, T1, T2 represent. And then phi 1 and phi 2 are just where in their oscillation did they start. And when we talk about like how far it traveled or how long it's been on, things like that. Just imagine like a speaker that's emitting just like a beep, like a speaker. Like the duration that it's been on would be T1 or T2. The distance from the speaker to the objects that were, or to the place that we're measuring at, would be X1 or X2. And phi1 and phi2 would just say, did it start when you turned it on? Was it at a peak? Was it at a trough? Was it at zero? So that's what these symbols represent. So the question then is, if both waves are present, how does the resulting superposition affect the intensity of the observed disturbance? So that's the question that we're trying to answer. Because in principle, we could measure the intensity from one of these waves, measure the intensity from, or we can measure the intensity from one of these waves, measure the intensity from the other wave, and we want to figure out, well, if they were turned on at different times, if they're located at, if they started at different places, if they had different phases, how would the resulting intensity change depending on where we start the object, how long they've been on, and so on and so forth. And you might think that they just add, but it's not that easy. So we want to compare the resulting intensity to the intensity that you would get if they were in phase. I.e., if their total phases were the same, we can figure out what the total intensity is pretty easily, because then the amplitude just doubles, and then the intensity is just the square of the amplitude, which is like 4 times the amplitude squared. So we want to compare the initial, and we want to compare the observed intensity when the phases are different to what it would be if they were totally in phase. So whatever our quantity is, or whatever our intensity is, should depend on the difference in their phases. The phase difference. By the way, the reason why we lined up all of this notation is because we're going to be using this a lot, like especially when we start talking about light. So this phase difference is just the change in phase between the two, and so we'll write it as phi1 minus phi2. You could have done phi2 minus phi1, doesn't matter. So now we need to start building our mathematical structure. So let's just say, let's suppose that I naught, this is an I now, not a phi, it's a Latin letter I, is the intensity when they are in phase. It's kind of the default intensity. So what we want to measure is what we want to calculate is we want a formula that will tell us, depending on how big delta phi is, how much is the intensity as it relates to the total or to the maximal intensity. We want, say, I as a function of delta phi, which should just be equal to, say, the maximal intensity. How come it doesn't matter if it's phi2 or phi? Because the cosine, that would just change whether it's a cosine or a negative cosine. And the intensity is basically a square, so it doesn't care about whether it's positive or negative. But that's a good question. Right, so we want to compare the intensity when they're out of phase with the intensity when they are in phase. And so, like, for example, we know that when delta phi is 0, when they are perfectly in phase, phi, or the intensity, should just be equal to I naught. But when delta phi is, when they're totally anti-in phase or anti-aligned, we know that the intensity should be 0. So we want to compare it with the maximal intensity, I naught. So we're going to just multiply I naught times some numerical factor, g of phi, or g of delta phi. G of delta phi will range anywhere from 0 to 1. It'll be 1 when delta phi is, when they're aligned, and it'll be 0 when they're anti-aligned. So this formula, this is what we're trying to find. We're trying to find g. because that'll tell us how the intensity changes with phase difference. So what do we know about G? Well, like I said, it varies between 0 and 1. That much is true because the intensity can't be more than the maximal intensity, and the intensity certainly can't be 0. Or it can't be less than 0 because intensity is a magnitude. We also know when it's 0 or when it's 1. So G of delta phi should be equal to 0 when they're anti-aligned. What does it mean for two waves to be anti-aligned, for two cosines to be anti-aligned? It means that their arguments differ by pi or 3 pi or 5 pi or 7 pi and so on. And that's because cosine of an odd integer multiple of pi is negative cosine, right? Or of x plus an odd integer multiple of pi is negative cosine. So this says that G of delta phi is 0 when delta phi is, say, pi or 3 pi or 5 pi, etc. Similarly, G of delta phi should be 1, i.e. the intensity should be the maximal intensity when they're aligned, which just means that the phases should differ by an even integer multiple of pi. And that's because if it's 0, 0 is an even integer multiple of pi, then that just means that delta phi is 0, so they're obviously aligned. But if they differ by 2 pi, that's just like going around the unit circle and then ending up back where you started, or 4 pi, go around, end up back where you started. So the argument is the same. Cosine of x plus 2 pi is cosine of x. Cosine of x plus 4 pi is cosine of x, and so on. So we already know some things about G. We just need to figure out what about the rest. So now we just have to do the work, right? So the total right now all we have are wave functions. We have f, f1 and f2, and we want to find like the total f. So to get remember that the intensity is related to the amplitude squared. It's proportional to the amplitude squared. So if we can add them together and then figure out what the amplitude squared is of the sum, that might help us relate it to the maximal intensity. So the total disturbance would be f1 plus f2, which is a times cosine of phi 1 plus a times cosine of phi 2. And so we can do some factorization. Cosine of phi 1 plus cosine of phi 2. And now we have to dig through our geometry textbooks. There's a trig identity that tells us how to relate the sum of cosines to the product of cosines. Cosine of theta 1 plus cosine of theta 2 is equal to 2 times cosine of theta 1 plus theta 2 over 2 times cosine of, oh, I'm running out of space, theta 1 minus theta 2 over 2. It's just a useful trig identity. You don't have to have it memorized. I looked it up. But it's a true trig identity. And so we can apply that here because we have cosine of phi 1 and cosine of phi 2. And so what we end up with is 2 times a just stays alone, times the cosine. And so look at this term. Well, in the numerator, that's the difference. And so the difference, we've already given a name. That's just delta phi. So we have 2 times cosine of delta phi over 2. And then here, this is the average of the two, right? So this is times cosine of phi average. It's just the average phase. So now we need to think about what this actually is saying. So the average phase is certainly changing, right? Because as time marches on, both T1 and T2 are going to change. So for example, T average is just T1 plus T2 over 2. And so if you increased, like if you waited one more second, both T1 and T2 would increase by 1 second. So the average time would increase by 1 second. Similarly, as you move further to the right, as you increase x, if you increase x by 1 meter, for example, both x1 and x2 will increase by 1 meter. So the average x will increase by 1 meter. So all this is saying is that this thing, the average phase, this changes with position and time. And by the way, the average phase is just a number, and so that doesn't change at all, but it is just the average of the phase constant. Sorry, the average phase constant is just the average of the phase constants. And so this right here, cosine of phi average, is just another harmonic wave. It just has a different, well, yeah, it just has a different phase. It has a different phase constant. Sorry, it has a different total phase. Its phase constant is different because it's the average of the two, and the amount of time that it's been on and the distance that it's traveled is different, but it's still just a harmonic wave. It's still just a cosine of 2 pi x over lambda plus 2 pi ft plus phi. It's just the x, the t, and the phi are now different numbers, but they still increase in the way we expect them to. This number, on the other hand, this doesn't change. And delta phi doesn't change because if you increase, say, x by 1 meter, then x1 is going to increase by 1 meter, but x2 will also increase by 1 meter. So the difference, x1 minus x2, stays the same. Similarly, for time, if you step forward by 1 unit in time, both t1 and t2 also step forward. So the difference still is unchanged. So this is just a number now. And so this is just, it's just like one big amplitude. It's just the amplitude now depends on what the starting conditions were, like how far apart from each other were the two speakers set up. How long after one speaker was turned on was the other speaker turned on? These are things that tell us the difference between the two sources, the two things generating the waves, and like what was the phase constant difference and so on. So what we can do is we can treat 2a cosine of delta phi over 2 as a new amplitude for a new wave. And the new wave has that as its cosine bit, and it has amplitude 2a cosine of delta phi over 2. And so our f total becomes a sub nu, it's the new amplitude, it's the amplitude of our new combined wave, times cosine of 2 pi times the average x position over lambda plus 2 pi f times the average duration that each one has been on, plus the average of the phase constants. And averages distribute over addition, by the way, so this should be fairly straightforward. So now, thinking back to computing intensity, I want you guys to remember that intensity is proportional to amplitude squared. So the intensity at some phase difference delta phi divided by the maximal intensity should be equal to the square of the new amplitude divided by the square of the maximal amplitude. Now the maximal amplitude occurs when they're perfectly aligned. So in that case, the amplitude just doubles. So the square of the new intensity is 4a squared cosine squared of delta phi over 2. And the square of the maximal amplitude is just 4a squared because the amplitude doubles, so a naught squared is 4a squared. And so what we're left with is what the formula that we wanted. I of delta phi is equal to I naught, so we're just solving this equation. We're moving the I naught over to the other side, times cosine squared of delta phi over 2. And so now you can check. And by the way, this is, I know that was a lot of work to get there, but this is an important result. You can check that this matches with our intuition. When they're perfectly aligned, we get that the intensity is just I naught. So try plugging in delta phi as 2 pi. Delta phi is 2 pi, then you get cosine squared of 2 pi over 2. Cosine squared of 2 pi over 2 is cosine squared of pi. Cosine of pi is -1, so cosine squared is 1. So you get that I of 2 pi is just I naught. And you could do this for the other ones when you have destructive interference. In that case, you get cosine of, say, 3 pi over 2 squared is well, what's cosine of 3 pi over 2? It's 0. So 0 squared is 0. So you have yet I of 3 pi is 0. There's an exercise in the Liber text that I suggest you take a look at. And by the way, most of this derivation, he did it a little bit differently in the Liber text, but most of this derivation or something similar to it is in the Liber text. So I do suggest you take a look at that, because this is tricky business, and I want you guys to make sure that you understand why we did what we did and how this, like what this means physically. 100%, please take a look. So that's what happens when you have, for this example, are we assuming both waves have the same amplitude? Yeah. So like I said, if they have different amplitudes, then the effect is just smaller, but the end result isn't very different. I mean, you could do the same calculation when they have different amplitudes. Like we assumed, by the way, that the amplitudes were the same, right? A and A. You could do the same sort of calculation for different amplitudes, but you don't really learn anything new. Also, by the way, there's an assumption here that they are traveling in the same direction. Notice that this is x plus 2 pi ft. X plus 2 pi ft. If one was plus and one was minus, which is what we're going to talk about in a minute, they're traveling in opposite directions. And then something else happens. So let's talk about reflections and transmissions. By the way, we're going to use this result that I put in a box a lot in the future, especially once we start talking about diffraction. So I have some GIFs that I'm going to refer to. Hopefully it doesn't break when I try to show you them. Let me put this over here. Okay, so this is great. Like so we talked about what happens when you have two waves traveling in the same direction and they're overlapping. Okay, fine. But waves do other things besides interact. Like waves bounce off of stuff, right? Like if I yell at my wall, I can hear it because the wave comes from the wall and hits my ear, right? So we need to understand that too. So if we have a wave that's, and we're going to talk about a one-dimensional wave, but this generalizes. If we have a wave that bounces off a wall, bounces off something, a one-dimensional wave, what we can say is that the leading edge of the wave, and I'll draw a picture in a minute, of an incoming wave to a wall is the leading edge of the reflection. And what that means is that the part that hits the wall first is the part that reflects first. And that should kind of make sense. Like the picture is actually, no, I don't have any GIFs. That's a bummer. So I'll just draw it. It's not hard to draw. So here's our wall. Let's say that we have a wave that is like this. So it's like lumpy on one side and it's pointy on the other side. It's going this way. It's going to reflect. And the question is what happens when it reflects? Well, it turns out after it reflects, depending on the type of wall, basically if the wall is soft or hard, the wave will reflect like this. So notice that the pointy end hits the wave first. So the pointy end is the part that comes out first when it bounces off. Now, you might ask, why is it inverted? Why isn't it in the same direction? And that I'm going to explain in a minute. But the only point that I wanted to make here is that the first part of the wave that hits the wall is also the first part that leaves the wall. And that's going to be true in general. And basically that just happens because of causality, I guess. Like it's just this notion that like events take place in certain orders, so it wouldn't make sense for this thing to just bounce off in the same direction, because this wall doesn't know about the left end of this wave when the right end is hitting it. So how would it know to like create that? Like basically waves aren't like rigid things that like stick together and bounce. That's the whole takeaway here. So now I have to explain why did I draw it inverted? So it turns out, and these are just properties that we can explain using this notion of a ghost wave, and I'll talk about that in a minute. When a wave reflects off of a fixed wall, the wave is inverted. So I have to explain what a fixed wall is. So the picture here is like, imagine tying this, imagine tying like a string to like something that doesn't move. So when the wave gets to that thing that doesn't move, in that sense, it's fixed, i.e. that thing's not going to move up when the wave encounters it. Whereas if it was attached to like a ring around a pole, as the wave comes in, it's going to pull the ring upwards, and it's going to reflect in a different way. So a fixed wall is a wall, or a barrier, really. A barrier that does not sympathetically oscillate. Sympathetically, you guys know the word that I'm trying to write, but I'm not going to write it because I'm out of space. Sympathetic oscillation is like a technical term, but I mean, I'm just using it in a colloquial sense, in that it doesn't move in the same way. And so, and we will explain why this causes inversion of the wave. But I'm just going over some details, and then we can talk about it in a minute, or explain it in a minute. When a wave reflects, I'm missing that word, reflects off of a free wall, free meaning that the object that it's bouncing off of is free to move up and down, say. No, this is not related to that. We will talk about that when we start talking about geometric optics. The wave is not inverted. So a free wall is the same. It's just a barrier that does sympathetically oscillate. So think like you tie like there's a ring around a pole, and we're ignoring gravity here, of course. A ring around a pole when the string is tied to the ring. When the string comes in, the string, comes in like this. It's going to yoink the ring upwards. So it can so the end that it's tied to can also move up and down. And so we have two separate cases when the boundary, the edge, the barrier, can't move, you get an inverted reflection. When it can move, you get a non-inverted reflection. And just as a note, for harmonic waves, and this is just a math statement, inversion of the wave is equivalent to a phase shift of pi, or by pi. And the reason for that is that cosine of x minus pi, so this is shifting the phase by pi, is just equal to negative cosine. And when we say it's inverted, we mean that it's the negative of the original wave function. So now we have to explain why. So why does this phenomenon occur? Well, there's this notion, this kind of mathematical trick that we use to understand this, called the ghost wave, which sounds spooky, but it's really not. And the point is that you can imagine this sort of reflection as, you can imagine treating the fixed wall as not a wall at all, but just requiring destructive interference at the wall, at that location. Where the wall was. So, and that would give you the same thing, right? You can imagine that you just have an identical wave that has, or you have a wave, something happening over here that's moving in the opposite direction, and whatever shape this wave has to be such that when they both hit the wall, when they both hit that location, they destructively interfere at the location where the wall was, and that would force the wall, that point, to stay fixed. It doesn't move up or down. And then they'll just pass through each other like normal waves do when they superpose. They interact for a brief moment, and then they just go about their way. And so you end up with an inverted wave because you're starting out with, let me draw a better picture here. You're starting out with a wave that gets, a wave that has to cancel out. So you start off with, okay, let me draw this better. So your wave on your string, it looks like, say, this. But we can imagine removing the wall and just replacing it with something that we know will destructively interfere with it at that point. So if this wave is going to the right at the same speed as this wave, they'll reach that center point at the same time. And because I've drawn it in such a way, because I've constructed this wave in such a way that they cancel out precisely at this location where the wall is, that would behave exactly as if that wall was just tied down, or that barrier was just tied down. And then, well, this wave will just continue on through because we're treating that wall as if it's not there, and this wave will become real. And so we see an inverted wave. So let me show you a GIF of this really quick. Oh no. It's like a normal force, but a wave. Not quite, but sure. It's loading, sorry. Okay, so let me show you instead what this looks like without the ghost wave, and then I'll show you what the ghost wave looks like. So here you have a fixed wall. It's coming in, it reflects. Notice that the point on the right doesn't change. It stays at the same height, and that's because it's fixed. And then it bounces off. Now hopefully, here we go. Okay, yeah, so here's a GeoGebra thing. So come on. There we go. Okay, so I'm gonna have it run with a fixed end. So here it's running. You have a pink wave. Okay, so the pink wave is the real wave. And notice that in order for oh wait, it's not actually showing the ghost wave. Not the ghost wave. That's not what I wanted. Yeah, okay, this isn't actually showing the ghost wave. I thought it would. So notice though that the red wave continues on through as if there wasn't a barrier there, but we just don't observe that. And instead, you have a wave that comes out from the left-hand side. Look at the blue wave that appears there. It's like it's moving left. That's the ghost wave emerging. Shouldn't it have to double the amplitude? But shouldn't it have the double the amplitude? One to destructively interfere, the other to go back in the opposite direction. No. So the point is that they in order for them to destructively interfere there, they have to have the same amplitude. And then when they separate again, well, they have the same amplitude, but in opposite directions. So now the wave is just inverted. Hopefully this GIF is helpful, or this GeoGebra simulation is helpful. I'll just let it run. Yeah, so the point is they cancel out at the wall, but then they just keep going after they pass the wall. One's going left, one's going right. All right. So the same can be said to be, we can do the same sort of analysis for, so this is a fixed end, for a free end. So if we have the same wave coming in, well, actually I'm not going to draw it as a wall. I'll draw it as like a pole with like a little ring attached to it, because that's like the best analogy here. And it's tight.
Sam, are we supposed to see your notes? Because we.
Oh yeah. Sorry. Good catch. Here you go. Right. So here we could do the same thing with a free wave. Here, when the wave comes in, the ring can move up, and so it will move up. And so in order to demonstrate that with a ghost wave, well, the ghost wave needs to be the same shape. So it has to be either upright. Has to either be an upright version or a not upright version of the same. An upright or inverted version of the same thing, because it has to be the same shape that comes out. But it can't be inverted because otherwise it would cancel out. So in order for this thing to move upwards, we have to have attached to it another wave. Oh, that's way too big. Or a ghost wave that passes through that's upright. And so when this wave passes through, when this ghost wave passes through, they come together and they constructively interfere at the point, or at the end, at the ring, and then they pass through and do their own thing. So let me show you again the GIF of the other one. So here is a normal reflection without the information. Notice that the amplitude does double, and the reason is basically it's being pulled up the entire way, and so you're pulling up on both sides of the wave. the reason intuitively why this happens. So let's look at the free end version of this. Reset. And let's run it. So here we have the wave coming in. So notice, by the way, that it's being pulled up. Like the ring is being pulled up. We're assuming the ring has like no mass here. Otherwise, there's some impedance that we have to deal with. But the ring is being pulled up by the wave because, you know, there's string attached to it and the string has tension in it, so it's pulling it up. And notice that the blue wave is the same as the red wave. They're the same in amplitude. They're just traveling in opposite directions. The blue wave passes through, and they both go about their merry way. And so what we're left with is a non-inverted reflected wave. And this happens because the thing that it's attached to can sympathetically oscillate. Let me go back to the notes. And so this isn't just a phenomenon that happens, by the way, for like barriers, right? So whether the string is tied to a wall or whether it's tied to a ring on a pole, either way, the wave doesn't actually continue on the other side. I mean, this notion of the ghost wave, this notion of the ghost wave is just it's just like a mathematical trick. It doesn't actually happen. There's not something happening on the other side. But you could imagine, like, what if you had like a really thin guitar string attached to like a really thick rope? Well, that rope's not like the thick rope's not going to move very much as the wave passes through it, the guitar string. It'll move a little bit, but it'll basically behave as if it were fixed. Or rather, I mean, well, I'm not going to assume that. It'll basically behave like a barrier, like because there's really nothing going through to the thick rope. It's basically all just would reflect. So in fact, whenever you have changes in medium, you can also get reflections. So this is just to say, medium changes also yield reflections. And this is the notion of impedance, by the way. If the impedance is different, then you'll have a reflection at the interface. But I'm not going to talk about that. So when a wave goes from, and I'll show you an animation of this in a minute. When a wave goes from a fast medium, a medium with a high wave speed, to a slow medium, a medium with a slower wave speed. And by the way, like different thicknesses of ropes will have different wave speeds because the wave speed, as I told you about last time, depends on the mass. And so if the mass is bigger, then the wave speed will be smaller. Yeah. If the mass is bigger, the wave speed will be smaller. So when this happens, there is still transmission going through the rope, but mostly, especially if it's like a really big difference in wave speed, mostly it'll just be reflected. And so the reflection is inverted. So the way to picture this is that like the really thin string attached to the really thick rope behaves very nearly like a fixed wall. And that's just because the really thick rope isn't going to move very much compared to the thin string. So you have like this. If this goes up, my hand's not going to move up. If like, you know, you have your wave here, this is only going to oscillate a little bit. So it'll behave a lot like as if it were just not oscillating at all, and then it'll just completely invert the reflection as if it were fixed. And so that's why you would end up with an inverted wave. So likewise, if your wave starts in a slow medium and goes to a fast medium, well, the fast medium is going to move more than the original wave was, which is what we see in the free case, because the ring moved more. So that would behave a lot like a free case. You still have a reflection, but now it behaves in a different way because it's easier to move the lightweight one than it is to move the heavier one. So in that case, a slow medium to a fast medium, the reflection is not inverted, and you'll get transmission in both cases. And the amount that's transmitted, depends on the difference in medium speeds. But we're not going to talk about that very much. Yes, I can answer that. Let me just finish writing. Right. So from a slow medium to a fast medium, the reflection is not inverted. And so the example here is a thin string attached to a thick rope. The rope is effectively a fixed boundary because the thick rope is not going to move very much. So to answer your question, or to explain it, so a fast medium, when I say fast medium, I just mean that the wave speed is faster in one medium than it is in the other medium. So like the wave speed in a guitar string is significantly faster than the wave speed in like a naval rope because the mass is smaller. And remember, the wave speed is the tension divided by the density. So if the density is smaller because it's thinner, this is linear mass density, then the wave speed will be much bigger. Yeah, this is precisely like light going from air to water, and this is actually why you get reflections off of glass, right? Glass is clear, so why does light reflect? Well, it reflects because the wave speed is different in glass, is different in glass from the wave speed in glass is different from the wave speed in air. Similarly, you get reflections off of water as well for the same reason. So let me show you some GIFs of this type of phenomenon. So here, we start off with a wave in a fast medium. Notice that the wave in the slow medium does move slower and the wave in the fast medium moves faster, but it moves less. And so it behaves like a fixed wall. And so you get an inverted wave. Now the wave is differently shaped. It has a different amplitude. Yeah, so if the wave speeds in two mediums are identical, there is no reflection. That's precisely it. That would be called impedance matching. Yeah, so the wave, the amplitude changes because the energy still has to be conserved, but the part that's reflected is inverted. Now, if we look at going from a slow medium to a fast medium, notice that the amplitude goes up because you have it's easier to move the right wave or the right medium, the thinner medium than the thicker medium. And the amplitude on the left is much smaller because almost all of the energy can be transmitted through. You don't get a very big reflection, but the reflection that you do get moves in the same direction. Notice that the boundary here moves up like the ring on the pole does, and so it behaves like a free medium, and so you get an a non-inverted wave. So it turns out that this notion of inverted waves, non-inverted waves, reflections, and so on can actually be really useful for constructing or for visualizing, or I guess just discussing a very particular and important wave phenomenon. So we can use this to discuss standing waves, or rather to construct standing waves. So standing waves in general are not actually waves, but standing waves kind of answer the question, what if identical waves travel in opposite directions on a string? Well, I mean, they're going to interfere with each other. That much we know is true. They'll add up. But they're both passing over each other, and so their troughs will sometimes align and sometimes they'll anti-align. How do sound waves get like muffled, stopped from echoing by those muffler thingies on the wall? We will talk about actually, will we talk about that? I mean, I know the answer, and you know what? I will answer it after lecture because it's not related, but it is a good question. Right, so the picture here is you have your string, you have your wave, they're coming towards each other, right? They're identical, except they're traveling in opposite directions. So sometimes their peaks will align with their peaks and their troughs will align with the troughs, and you'll get constructive interference. But sometimes the peaks will align with the troughs and the troughs will align with the peaks, and you'll get destructive interference. So what happens when you have this phenomenon occur is you get something called a standing wave. A standing wave isn't quite a wave, but it kind of looks like one. So that's why it has the name. There's actually a nifty standing wave on a string animation in the LibreText. I'm going to show you an animation that I found from Wikipedia. So look at the wave. Look at the green wave. The green wave is moving to the right. The blue wave is moving to the left. The resulting wave, the superposition of these two waves, is the red thing. Now, I'm not calling it a wave because it's not quite a wave, because it doesn't move. But it kind of looks like a wave, but it just looks like something oscillating in time and not really moving in space, which makes it not very wave-like. So when they overlap, when red and blue overlap, you get constructive interference, and that's when the magnitude is biggest. And when they anti-overlap, when the peaks and troughs align, you get destructive interference. And so this is the kind of thing that happens. Now the question is how do you actually make these, right? Oh, yeah. So how do you make these things? Well, I mean, in the real world, there aren't just infinite waves that you can just use. But the trick is that we can use, like if we wanted to like make this in a lab, we can use reflections to form perfectly identical waves traveling in opposite directions. Assuming no energy is lost, what you can do is you can like start a wave if you have two barriers. Oh, my computer just shut off. If you have two barriers, say two fixed ends or whatever, and you start a wave going this way, well, it's going to and you start a wave that's for the whole thing and it's traveling to the right. Well, the part that's near the end will reflect and form another wave traveling to the left. So you'll end up with two waves going in opposite directions, bouncing off and interfering with each other. We're referring to how the waves look, they're not moving, or the fact that this superposed wave is just oscillating and not moving. It's okay, so they're waves in the sense that they satisfy the wave equation, but they're not waves in the sense that they don't change in position, like their position, like they don't travel. So you might distinguish standing waves from traveling waves. Traveling waves are what we really think of when we think of waves. Standing waves are a wave phenomenon, but they're not traveling waves, i.e. you can't write them as f of x plus vt or f of x minus vt. That's just not possible. Right, so we can form these. We form standing waves by reflecting off of two boundaries. Either fixed or free. And whether the wave is fixed or free, it doesn't matter. You're still getting a reflection. It's just the reflection might be different by a different, or the wave might have a different phase. Remember, for a harmonic wave, of a reflection, an inverted wave has a phase difference of pi. So you have to account for that fact. Now, we're just going to do some quick maths just to show you how this sort of phenomenon arises. So let's suppose that F1 is a wave that's traveling to the left. We're not going to worry about reflections or anything yet. We're just going to say that we have two waves traveling in opposite directions that are identical. This is A times cosine of 2 pi x over lambda plus 2 pi ft plus phi 1. And then we have f2 of x and t. This is A cosine of 2 pi x over lambda minus, oh, let's do minus on the first one. So we have minus, so the first one, we have 2 pi x over lambda minus 2 pi ft plus phi. This would be a wave that's traveling to the right. Remember, this can be written as x minus vt. You'd have to do some factorization to see that, but it can be written as as something of x minus vt. And then the second one will be plus 2 pi ft plus phi 2. Now, the important point here is that these waves are identical. They're just traveling in opposite directions, and those opposite directions are captured by the difference in signs there, SIG and sign. So if it happens to be the case that phi 1 minus phi 2 is equal to pi, like for example, if they were formed by an inversion, by a fixed end, then we can use standard trig identities like we did before. F of x and t plus f2 of x and t would be equal to, and I'm going to skip the algebra here, 2 times a times sine of 2 pi x over lambda times sine of 2 pi f t. So here, this first term, these things are multiplied together. I'm encapsulating the a and the sine term. This is like a snapshot of the wave. Like if you set t equal to 0, and then plotted x, it would look exactly like this function, right? And then this part describes just the oscillation of a single point. i.e., if you just looked at a single place, a single x position in x, say x equals 0, and you just plotted how that place oscillated with time, it would look like this one. And note that there's a 2 up front because the amplitude is doubled. When they perfectly constructively interfere, you get 2 times the amplitude. When they destructively interfere, you get 0. So this isn't a wave because you can't write this as x plus vt or x minus vt. Instead, this is something else. It's an oscillating wave phenomenon. But what we can do is we can treat, well, let me write that. This is not actually a single wave. Cannot be written as f of x minus plus vt. So standing waves are only constructive interference and also they are also destructive interference. Now let's think about why. So the standing wave can really be viewed as just a snapshot of a wave where the amplitude changes with time. So the way to do that is just to, let's call this f of x and t. The way to do that is just to reorder the terms and then group. So this would be 2 times a, and then I'm going to write the sine term first, or the sine of the one with t in it first. I'm going to put parentheses around that, times sine of 2 pi x over lambda. So we already established that this term here is just like a snapshot of one of these waves. And then notice that the amplitude of that snapshot is just the thing that's multiplying the sine. But importantly, that thing that's multiplying the sine depends on time. It's time dependent. And so what this looks like, going back to the GIF, if you just look at the red one, it looks like just a snapshot, and then you're changing the amplitude with time, and you're also making it negative, so it inverts. So it just looks like just a regular snapshot of a wave, except now the amplitude is changing. And so we have destructive interference. That destructive interference occurs when the amplitude is 0. And we have constructive interference. That constructive interference occurs when the amplitude is twice the amplitude. But the point is a standing wave really is just, it's not even a wave because it doesn't travel. It's just like a single, it's just like a sine or a cosine, whose amplitude changes with time. That's what a standing wave really represents. But it turns out the standing waves are kind of nifty. Oh, did I have one more GIF? No, I didn't. Okay. So amplitudes are nifty, or not amplitudes. Standing waves are nifty because, sorry, staring at down at an angle kills you. So phi only had to be equal to pi because it makes this sine and cosine. It makes these both sines, and it makes the formula nicer. That's all. The difference in, like, if it was 2 pi, then this formula would be slightly different. But the bottom line is that you would have something that looks like a snapshot and something that looks like a time-varying amplitude. Those might be sines, those might be cosines, but at the end of the day, it's still like a sine or a cosine whose amplitude changes like a sine or a cosine. That's all. It's just this is the simplest one that makes the trig the nicest. So why do we care about standing waves? Well, it turns out that in musical instruments, for example, in lasers, wait, we originally had cosine and then that's the trig identity. Yeah. Yeah, that's a trig identity thing. So in musical instruments, in lasers, in a lot of different phenomena, like guitars or woodwinds or strings, woodwinds, whatever, standing waves can be used to extract something. So as you can probably tell, the standing waves can oscillate a lot, right? Like your only input is green, or say it's either green or blue, but you get like big swings in amplitude out. So it turns out that like if you can couple your oscillation, your standing wave, with something else, like for example, if you put a string in air and then you vibrate the string, the string's going to bounce off the air, and it's going to cause that air, it's going to propagate waves into the air because it's buffeting it over and over again, and it's going to make waves travel in the air. And those won't be standing waves, those will just be traveling waves. So we can use standing waves to either absorb energy or to extract energy in a certain pure way, a way that has a particular shape. In the case of a woodwind or a guitar is the easiest example because it's a wave on a string. The standing wave has a very particular frequency. Notice that it oscillates up and down. This example oscillates up and down at a very precise rate, and it depends on the distance between the two ends. Notice that exactly 1.5 oscillations fits between the two ends, right? If it wasn't 1.5 oscillations, if it was say like 19/18 oscillations, it wouldn't fit. So by using a particular shape of a wave, or rather by using a particular length of your string, you can choose what type of wave you want to produce on your, what type of standing wave to produce. And so that's why like the length of a guitar string affects the sound it produces, because standing waves can only form in certain discrete sizes, frequencies, and so it'll produce certain sounds. So for example, if the standing wave was oscillating 500 times a second, it would bounce against the air 500 times per second. And that would produce a sound wave that we hear that is a frequency of 500 times per second. These aren't parabolic, these are sinusoidal. Similarly, in a laser, what you do is you excite a whole bunch of atoms that produce waves of a whole bunch of different frequencies. But you can tune your cavity, is what it's called, so that only certain types bounce back and forth, and they amp each other up. They light amplification by stimulated emission of radiation. And then you just let just a little bit out, and the stuff that comes out, this is in a standard like old gas laser, the stuff that comes out is of a very, very pure type of oscillation. It's a very specific frequency, just like how a guitar makes a very specific frequency when you pluck its string. So standing waves are super useful. Like you know, without standing waves, we wouldn't have lasers, we wouldn't have music, we wouldn't have like anything. That's not true, not anything, but there's a lot of things that rely on this notion of standing waves. So let's talk about it in more detail. So I mentioned when talking about oh no, I was trying to show you the GIF, but I never changed to share. When talking about the guitars, the size of the string depends or affects the, how do I want to phrase this? Like the wavelength and the frequency of the wave that you put on the string has to be related to the size, like the length of the string, in order to get the appropriate oscillations. And I just want to show you, just because I didn't actually share. Notice how this string is precisely what like 1.5 oscillations long. If it weren't 1.5 oscillations long, you wouldn't get a standing wave like this. Okay, hold on, that's weird. Right, okay, you wouldn't get an oscillation like this if the string wasn't exactly 1.5 oscillations long. That's the important part. Okay, let me go back. So clearly the length influences it. So now we have to talk about this notion of harmonics. So harmonics are basically a way of counting let me write this out a different way. Harmonics tell us how many oscillations there are in a standing wave cavity. A standing wave cavity, by the way, is just like the thing between the two ends. So you have like a fixed end and a fixed end, or a free end and a free end, or a fixed end and a free end. That's the cavity where your string is. Like the standing wave cavity in a guitar is just it's the string between one end and the other end. And so the harmonics, like harmonics are numbered. There's the first harmonic, second harmonic, and so on. Those kind of count how many like bumps there are and how quickly it oscillates. So this can be done by sort of counting the antinodes. And I'll explain what an antinode is. An antinode, I'll explain that in a picture in a minute. But we need to talk about what the nth harmonic is. So the nth harmonic of a cavity, a standing wave cavity, this is a description, by the way, of like the cavity. This isn't a description of, or the nth harmonic is a type of wave that exists, a type of standing wave that exists in a standing wave cavity. The nth harmonic is the standing, oh, sorry, I skipped something. I need to talk about the fundamental harmonic first. The fundamental harmonic is the standing wave in the cavity with the fewest antinodes, or with the fewest bumps. Antinodes, by the way, are just bumps. And the nth harmonic, so you might say the fifth harmonic, the ninth harmonic, whatever, the fourth harmonic, is just the standing wave with frequency n times the fundamental harmonic frequency, n times higher than the fundamental frequency. The fundamental frequency being the frequency at which the fundamental harmonic oscillates. So if it goes up and then down once every 2 seconds, the frequency would be 0.5 hertz. So the fifth harmonic in that case would have a frequency of 2.5 hertz. It would go up and then down 2.5 times per second. So like I said, an antinode is just it's just a fancy name for a bump. A node, on the other hand, is the place where the string doesn't move. So looking back at our GIF, if we look at red, right in the middle of this GIF, the string isn't moving. It's just, oh, what just happened? Okay, right in the middle, the string isn't moving. It's just staying fixed, and it's oscillating on either side, but it's staying fixed in the middle. That would be a node. The places where the bumps are occurring are antinodes. So nodes and antinodes are locations along your string, for example, or in your air cavity for a woodwind instrument. So we can just draw pictures. So if our cavity has two fixed ends, so not quite. So I mean, are there 4 nodes or 4 antinodes? Yeah, so kind of sort of, except the ones in the end only count for a half of a node for reasons that are never obvious. So if we have 2 fixed ends, remember that what these ends do is they tell us what can happen on either end. So in this GIF that I've given, this would be an example of a free end. Notice that on the left hand and right hand side, the end is moving up and down. If these ends were fixed, then the end would be fixed. Like the ends would not be able to move. Oh, sorry. I don't know why this keeps happening. Yeah, the ends wouldn't be able to move if both ends were fixed. And so it would oscillate like inside, but not on the ends. Whereas here, it's oscillating on the ends. So this would be 2 free ends. So I'm just going to draw some pictures. These will be terrible, and I'm sorry about that, but I'll do my best. So if we have 2 fixed ends, here's our cavity between these 2. We have our string between them. So the fundamental is it's the standing wave with the fewest antinodes. So it's going to, so we know that the string has to be fixed on either end. We need to form a wave. Well, so we could do this, and then it could like oscillate back and forth like this, but we could do even better, actually. We can do even fewer antinodes. In fact, if we just do a wave that looks like this, oscillates up and down, that only has 1 antinode. That's the fewest number of antinodes. Antinodes come in discrete bundles. You can't have half an antinode, except at the ends, which is a separate thing. But here, there are no antinodes at the end because these ends are fixed. They're not moving. And so this would be the fundamental harmonic, often sometimes just called the fundamental. Notice, by the way, that the wavelength here is twice the cavity length. So let's call this distance L. then the wavelength is 2L. And we can figure out the frequency by relating the wavelength to the wave speed. We can do the same thing. What about the next harmonic? Well, the next harmonic should have one more antinode. So this has one antinode, the next one has, yeah, there are 2 nodes in this example. Or again, the ends kind of give you half. They kind of give you half. So there's like 1 node here. But again, like really, the number of nodes isn't super important. The important part is that there's exactly the important part is that this is the fewest number of nodes of antinodes. The next one, if this has 1 antinode, then the next one would have to have 2 antinodes. Again, it's fixed on both ends, so there's no oscillation there. So what can we draw that has 2 antinodes? Well, we could draw this. This has precisely 2 antinodes. So this would be again, the length is L, and the wavelength here, well, this is 1 full wavelength, right? It goes up, then comes back down, then goes back up. This is 1 full wavelength, so the lambda here is L. The wavelength is L. This would be the second harmonic. And by the way, because the wavelength is half as big, V, wave speed, is lambda times frequency. So frequency is V over lambda. So because the lambda here is twice as big, sorry, the lambda is half as big, the frequency is twice as large. So this makes sense. This is the nth harmonic because the second harmonic has a frequency twice as large as the frequency of the fundamental because its wavelength is half. We can do the same thing for 2 free ends. We can draw pictures. And by the way, the third harmonic would just have 3 bumps. And its wavelength would be 2L over 3. There's 1.5 wavelengths per L. So 2 free ends, well, the ends are, as the name implies, free. So that means that they should be moving up and down. So for example, what's the, so we could draw something that looks like this, right? That would have free ends because then it would oscillate back and forth. But we want fewer. Well, what's the fewest that we can do? The fewest that we can do is this one. Now this has like one antinode. And the reason I say it's 1 antinode is because the ends only count for half, really. And the reason why the ends count for half, there's a good reason for it, but it's just a good shorthand. And so this oscillation goes like this, oscillates down and then like this. So this would be the fundamental. And again, this has precisely half a wavelength in it. It only has half of the oscillation. So in this case, lambda would still be equal to 2L. Okay. What about the second harmonic? Second harmonic? Well, so if this has 1 antinode, we need 2. So we still know that the ends have to be antinodes. So, but we need 1 more node in the middle, or 1 more antinode in the middle. So we can draw it like this. Oops, that's terrible. Actually, that's not terrible. That'll do. And so you still have the antinodes on the end, and you have 1 more in the middle. And so in this case, lambda is just L. I was brain freezing for a minute. And so this would be the second harmonic for the same reason as above. This is lambda equals L here because it goes down, then up, and then it's back where it started. How many nodes for this? Yeah, so this has 2 nodes. For 2 free ends, the number of nodes is just fixed. This has 1 node, this has 2 nodes. When you have 2 fixed ends, the number of antinodes is something that's like easy to figure out. And then there's the final example, the redheaded stepchild. I have nothing against redheads, it's just a meme, which is 1 free end and 1 fixed end, which is a little bit harder, and it always throws a wrench in things. So we know that 1 end should be fixed. 1 end should be able to oscillate. So it could look like this, where it ends at an antinode and starts at a node, but the smallest one is just this. the one with the fewest nodes, fewest antinodes, would be one that just it's attached on one end and it's just the other end just moves up and down. That would be a totally fine wave. And so this would be our fundamental because this has, half an antinode. So the next one should have one more antinode. It should have an antinode somewhere in the middle-ish, and it should also have an antinode on the end. So this next one should have like 1.5 antinodes. So the picture is this one. So it has an antinode here, and then it also has another half an antinode on the end. So here's where things get messy. So this has a wavelength of 4 times L. It only goes through a quarter of an oscillation. It goes up, and then it misses the down, and then the down again, and the up again. So this has a wavelength of 4 times the wavelength. This one has a wavelength of 4/3 L. So this would be the third harmonic, because this and that's because you can fit precisely 3/4 of a wavelength in one thing. Like the rest of the wavelength is over here, right? So it's 3/4. So this would be the third harmonic. And this is to say that when one end is fixed and one end is open, there is no second harmonic. It doesn't exist. Does it work when antinodes are typically in discrete bundles? Where do we see instances of one free, one fixed? This is instances of one free, one fixed. So this is the third harmonic, which is to say that you can't form a standing wave where one end is fixed and one end is free that has twice the frequency of the fundamental. It's not possible because the fixed end always has to be fixed. The free end always has to be free. There's no wave. It's called the third harmonic because, remember, the nth harmonic is the harmonic whose wave has frequency n times higher than the fundamental frequency. So the wavelength is 4/3 L because L is equal to 3/4 times the wavelength, right? You could fit another quarter of basically only 3/4 of the wavelength is between L, right? To get a full wave, it would need to go extend out another quarter of the wavelength. And so because L is 3/4 the wavelength is 4/3 the length L. And this is the third harmonic because, again, frequency is V over lambda. And so the frequency here is V over 4L, whereas the frequency here is V over 4/3 L, which is 3 times V over 4L. So the frequency of this wave is 3 times bigger than the frequency of the fundamental. Hence, it's the third harmonic. So here, there is no second harmonic, which is very strange. But you can observe this if you, like, for example, if you, there aren't actually a lot of examples of musical instruments like woodwinds that behave this way. I think an oboe behaves this way. So if you produce the lowest note on an oboe, you can't produce a note that's twice as high unless you change it by pressing keys. Yeah, such a standing wave doesn't exist. Like the second harmonic doesn't exist. There is no standing wave that has that frequency here. So there's a formula actually for figuring out wavelengths. And I might run a few minutes over because I just want to, actually, no, we're almost done. For the wavelengths of harmonics. Now, the numbers that I'm about to write are not necessarily related to the harmonic number. So when both ends are fixed or free, the wavelength of the nth harmonic is 2L over n, where L is the length of the cavity. The wavelength for the nth, not for the nth harmonic, the wavelength for the 2n minus 1th harmonic, for one end fixed and one end free, is 4L. So divided by, and you can figure this out by drawing pictures and measuring basically, divided by 2n minus 1 for one end fixed, one free. So maybe I should actually write lambda 2n minus 1, because there is no lambda. Lambda 2 might be the second harmonic, but there is no lambda 2. Because there's no, these are for integers n, for positive integers n. So to plug this in, if you wanted to know, say you have both ends fixed, right? If you wanted to know, say, the 9th harmonic, the wavelength would be 2L divided by 9. Now here's the trouble. For one end fixed and one end free, you might say, okay, what's the wavelength of the second harmonic? But then you would look, okay, so I need to plug in some integer n, but I can't plug in it. There is no integer, positive integer, such that if you multiply by 2 and subtract 1, you get 2. So there is no second harmonic for one end free and one end fixed. However, if you want the third harmonic, you just replace 2n minus 1. That is when n equals 2. You replace that with 3. And so then your wavelength of your third harmonic is 4L over 3. So there's a few examples that I linked or that I referenced in the lecture notes. I will refer you guys back to those, and we'll call it quits here. So